Hello, my name is Berkay Karacar. I'm a research assistant in our department. And today we will going to construct our second experiment in EE313, which is single-stage MOSFET amplifiers. So, as you can see here, we constructed the first circuit given in your manual, which is a common source amplifier with a degeneration. And in the experiment, the required constraints are little different than the constraints given in your preliminary work. So, according to our constraints in the experiment, we figured that we need to connect a 1.2 mega ohm as RG1, which is here, and then we need to connect 4.7 mega ohm as RG2, which is here, as you can see, this one. And then we need to use 8.2 kilo ohms for RD, which is here. As you can see that this is connected to the fifth pin of MOSFET, which is drain pin. And then we connect 100 ohm as RS, the degeneration resistance, to the source, which is the fourth pin of our MOSFET. So in the circuit, as you remember from the first experiment, we need to connect the seventh pin of the MOSFET, which is the bulk pin, to the ground. And you can see that the gray wires are used for the ground connections. And so we use blue lines as input, and VD connection and input. Here you can see this is the input of the signal generator, and also we connect the ground parts of the multimeter, the DC generator and the signal generator, and also oscilloscope to the ground with gray wires. So in here, I would also like to remember you that we use the third pin, as in the last experiment, we used the third pin as gate, fourth pin here as source, and the fifth pin as drain. So there's an additional circuit element in this circuitry, which is capacitors. We use 10 microfarad capacitors as coupling capacitor. And we need these capacitors because there's a DC connection here, and we need to eliminate the DC offset of our circuitry, so we use these capacitors. And if you use a low capacitance like light picofarad or nanofarads. Now we will continue with the second question in the first part of the experiment, which is DC operation, examining the DC operation of our circuitry. So I will connect this to the gate, to the third pin of our MOSFET, and as you can see, we get a 2.85 or 80 around DC voltage here. And then I will connect this to the third pin of the MOSFET, which is the source pin, and sorry, it was fourth pin, and now we get 100 millivolts around, which is actually which we expected because current is 1 milliampere. So as RS is 100 ohm, then the voltage on the RS source resistance is expected to be 100 millivolts. So now I will continue with the fifth pin, which is drain of our circuitry. So as you can see, now we get 6.40 volts. So we find the gate voltage as 2.8 volts, and drain voltages as 6.4 volts, and the source voltage as 100 millivolts. So you can find the gate to source and the drain to source voltages from those measurements, and also you can find the operation of the MOSFET from these voltages, from these measurements. So as expected, there might be some differences from the simulations, so you should be careful about the reasons why there's differences in the real life experiment and the simulation. So in this part of the experiment, it is required from us to connect a 10 kilohertz voltage to the input. And now, from here, I will apply sine voltage from waveforms, and then from parameters, I will adjust its requirement, which is 10 kilohertz. And I will give amplitude as 100 milli peak to peak. And I adjust the offset as 0 volts and the phase as 0 degrees. Now, from channel, this is important. You need to convert to output load as high Z, which is really important as you learn from your other courses, previous courses. And then I will convert output as on. So here you can see that in our oscilloscope we see the voltages, which is the yellow one as the input voltage and the green one as the second connection and the output connection. So here from trigger we need to adjust it from horizontal and trigger. So be careful that the source of your trigger should be 1 or 2, not the other ones. It will be beneficial if you use the output as the source here. And now we adjust the trigger. So here we want to add some measurements. From measurement, you can add some measurements, and I will start with the frequency measurement. As here you can see the frequency measurement of the yellow, which is the input, which is 10 kilohertz as expected. And now from the source I will choose the output and type as peak to peak, and I will add it. As you can see, it is 850 millivolts. And now also I will add the peak to peak voltage of the input. So as you can see, we find the output peak to peak voltage as 850 millivolts, and the peak to peak voltage of the input is 100 millivolts. So thus the gain of our circuitry, the amplifier, is 8.5. And you can find the GM from here with the theoretical result, with the theoretical expectations. So now we will find the output swing, which happens when the output voltage reaches its maximum and minimum. So when you increase the input to a value, then the output will reach its maximum and the minimum, so the output signal will be distorted, as you will see in a minute. So now I am increasing the input voltage here. And I need to also scale the output. Now I am increasing the input voltage. and also I am so still increasing the input, and now you may see that here we reached the minimum, so the output signal cannot go below this value, so the signal loses its sinusoidal behavior here. It is like, as you can see from here, it is 1.6 peak-to-peak input voltages, then the output current, output signal is distorted in here. So let's look for the, so I will close the input, and here we can see that the scale of the output signal is 5 volts, and as you can see here we reach the minimum value of the output signal, which is -5 volts, about -5 volts, and also the peak-to-peak value is 11.2 volts. So the output swing of our circuitry is around like plus 5.5 volts to minus 5.5 volts. So since you may ask that, since we are not applying any minus voltages to circuitry, how we can get a minus voltage here? And the answer is actually pretty simple, that since we are eliminating the DC offset by our coupling capacitance here, so now we get the minus voltages for the AC signal. Now we will continue with the examining the FFT behavior, which is fast Fourier transform. So we will examine the frequency behavior of our signals. So you can do that from here, the math, and here you need to choose FFT as the operator. And so since we are interested in this output signal, we use sec2 as the source, and we adjust the span as 1 kilohertz, which is the scale here, and the center frequency as 50 kilohertz. So you can see the first one corresponds to 10 kilohertz, and the second one corresponds to 20 kilohertz, and the third one corresponds to 30 kilohertz, and so goes on like that. And now you can see that we have a peak at 10 kilohertz as expected, since our output signal is 10 kilohertz. And now you can see that we are applying 100 millivolts peak to peak as our input. Now we will increase this as we increased before to find the output swing. And as we increase, you can see that the fundamental frequencies, harmonic frequencies, which are the multipliers of fundamental frequency, are increasing with the increase in the input. This is mainly caused by the distortion in the signal, since as we see before, there's a distortion in the signal when we increase the voltage. So as we increase the input voltage, the output voltage will turn to a square wave, and you can see that as you know that a square wave has many frequency components, and you can see that in the FFT function there are many peaks in the frequency. So now it is required from us to find the input and the output resistance of our circuitry, which is a challenging goal. However, it is actually pretty simple to solve it. So now we connect a series resistance to the input to find the input resistance, and when we change the pot resistance, we expect the output voltage to decrease, since the input voltage of the circuitry changes with the pot resistance. And when we find out a voltage value which is the half of what we expected and what we measured before, so that must be the input resistance of our circuitry. And we can continue with the output resistance in the same way. However, this time, instead of connecting the pot resistance to the circuitry as a series connection, we need to connect the pot resistance as a parallel connection to our circuitry, and we will do the same as we did in the input resistance. Find out the output resistance with a simple simple adjusting. So now we will continue with the second part of the experiment, which is common drain amplifier. So you can see the circuit figure of a common drain amplifier in your preliminary work and in the manual, which is figure 2. And as a common knowledge, in a common drain, we connect the drain pin of the MOSFET to the drain voltage. So here you can see our circuitry. So as our requirement, we want 0.05 half gain, and in this circuit drain configuration. So for that one, we select 8.2 mega ohm for the RG2, and we select 4.7 mega ohm for the RG1, and 10 kilo ohm for the drain voltage. And so as you can see, the gate voltage is 3.4 volt, and the source voltage is about it is still increasing. So because of the capacitance, we expect some delay in the circuitry, so we need to wait for the actual result. So here it is 1.25 volts, and the drain voltage is, as expected, it is 20 volt, which is the drain also the VDD voltage. So let me explain the circuitry a little. So again, the gray wires are for the ground wiring, and we connect the bulk voltage of the MOSFET, which is the 7th pin, as with a gray wire to the ground. And here the blue lines are for the input and the VDD voltage. So the white wires are for other type of like oscilloscope connections. So the all ground parts of the all multimeter, the signal generator, the DC voltage generator, and the oscilloscope are connected to the ground with gray wires. And also let me remind you that we need to use the 1x of the oscilloscope connection, so it is also arranged. So now I will continue with the measurements, the other measurements of the circuitry. Now we will continue with the input signal, which is 10 kilohertz. And here you can see that the peak-to-peak voltage of the input, which is the yellow one, is 1 volt. And the peak-to-peak voltage of the output, which is the green one, is is 60 millivolts. So the gain is approximately 0.6, and the frequency is, as you can see, is 10 kilohertz. And we also adjust the trigger according to that, as we mentioned before, how to adjust the trigger. So I will also let you to see with adjusting the horizontal scale. So now we will continue with the output swing operation. So for that one, we will come to the input arrangement of the signal generator, and we will increase the peak-to-peak voltage that we apply, and we will look for any distortion in the output signal. So we are still increasing. Let me also arrange this one, because maybe like this, not like this. So also can click this one. So here you can see that there is a distortion in the output signal around when we apply 6.4 peak-to-peak voltage. So the output swing is also here. You can see that the peak-to-peak voltage of the output is 3.5 volts. So the output swing is 3.5 volts. So also let me remind you that the requirement for your preliminary work, the required constraints of the circuitry is different than ours. So since, as I said before, the requirement in the experiment was 0.6 volts, 0.6 gain. However, your requirement might be different than that. So the resistance values for you might be different than ours. Furthermore, for R-in and R-out, as we did in the first part of this experiment, you need to connect a pot resistance seriously to our circuitry to find R-in, and parallel to the R-out, to output part of the circuitry to find the R-out. And you need to look for the half of the output voltage, and then you need to measure the pot resistance. So this was the second experiment of EE313, and I hope you enjoyed this. I hope that you enjoyed this video. If you have any questions, you can directly connect with me and other EE313 assistants to ask any questions. So take care, guys.